Swayam Prabha. Digital India. Educated India.
So, welcome to the second lecture of the second module on processes and threads. So, if you recall, in the previous lecture we had discussed the basic notion of a process and a few other things like what are the different states of a process. We also mentioned that in general in a system at any given time there can be multiple processes in various states of execution. So, one of the responsibilities of the operating system is to maintain information about the processes, in which states they are, and to manage them in some way. So, the title of today's lecture is keeping track of the processes. Let us see. The first thing is that I said that in general there can be more than one processes running on the system. The first question that arises is how does the operating system maintain information about the processes. Now, there is a data structure which is maintained by the OS that is called the process control block or PCB. This is the basic data structure that is maintained for each and every processes in the system, and that contains all the relevant information that needs to be maintained or kept about a process. Now, we shall see that as you know that the processes can be in various states like the ready state, running state, block state and so on. So, multiple number of processes which are in the same state are typically chained together in the form of a linked list, like for example, the PCP of one process will be linked to the PCP of the next process, which will be linked to the PCP of the next process. In this way, the last process will be stored null as the next pointer. Now, so the idea is all the process control blocks of the processes that are in the same state, they are typically kept like this as a linked list, and this linked list is also sometimes referred to as a process queue. We shall see later that when we talk about process scheduling, CPU scheduling, dispatcher, so the concept of this process queue will again come into the picture. For instance, whenever processes are in the block state, there can be various reasons why a process is in the block state. A process can block maybe because it has initiated an input or output operation. So, until and unless the IO operation is complete, it cannot continue, or it can wait for some other event like I mentioned about semaphores and other kinds of locks. There can be multiple processes which are waiting on the same semaphore. So, block state, all the processes, they may not be maintained in the same queue. There can be multiple queues corresponding to the different events. So, for every different event, typically a separate list is maintained. Why? The reason is simple. Suppose a particular event E1, there are 3 processes which are waiting for that event E1. Okay. Now, later on when event E1 comes or event E1 occurs, you can straight away go to that corresponding list for E1, which are the processes that are waiting, and you can wake the processes which are waiting there. Okay. But for the ready state means the processes are all ready to execute once you give the CPU to them. They are typically chained in a single list. There is no multiple list for the ready state processes. Okay. Fine. Now, let us now see what are the typical entries that we require to have in a process control block or PCB. Well, the first thing I said that we need to maintain a linked list of the PCBs to maintain the different lists or the queues, process queues. So, the first thing it should contain is a pointer to the next PCB in a list. Now, for those of you who are familiar with pointers, you know pointer is nothing but it is the address of some memory location. The PCBs are typically stored in memory. Inside a PCB there will be one field which will contain the address of the next PCB. Similarly, in the next PCB that field will contain the address of the third PCB and so on. For the last PCB, the next address pointer or the next PCB pointer will be stored with a special value which is called null. Null means there is no other PCB after this. Okay. Now, in addition to that, most important thing we need to maintain in which state the process is, the process state, whether it is in ready, running, blocked and any other state. Okay. Now, we mentioned earlier in the last lecture that when the processes change the state, sometimes a running process may have to be moved to the block state or the ready state. So, for those process what do we need to do? The process was already running, right. In the CPU there were so many registers, the registers contained some temporary variables for the processes, results of the calculations that are going on. Similarly, the program counter contains the address of the next instruction to be executed. So, when we suspend a process temporarily, the contents of all these registers must be saved, all CPU registers and most importantly the program counter, because later on when the process wants to resume, you will have to resume from that exact point where you suspended the process, which means all the registers have to be restored back to their original values, program counter initialized to that old value, so that it can start from the instruction where it was suspended. So, you need to save or store information about the program counter and all the CPU registers. The reason I have said, so that you can save a process and resume it correctly later on, and this process is called context switch. I said whenever you switch from one process to another, you have to save so many information and you have to restore this information again for the next process. And as you all know, a process in execution is allocated some space in memory. So, the OS must also keep track which part of the memory is currently allocated to a process. Okay. So, some information about memory allocation must be there, because let us say sometimes in the future because of memory shortage, some of the processes may have to be swapped out to one of the swapped ready or swapped block states. Then the memory that was currently being used by that process can be deallocated or freed, so that other processes can use them, right. In addition to the memory, you need to store the list of all the files that are currently open by the process, because when you open a file, you normally read or write from the file in a sequential order. So, you have to maintain which file was opened, the file pointer, and currently where in the file you are reading or writing. So, all those information must be there. In addition, if the process was using some IO device, then that information must also be there. And the next point, of course, we shall be discussing the detail later. There is something called CPU scheduling. So, some relevant information that can help in the CPU scheduling can also be stored in the PCB. Because you see, CPU scheduling means whenever the CPU becomes idle, the OS must decide, that means the dispatcher module, which of the ready processes must be given the CPU next. Now, there can be a number of different policies, and for those policies to work, you have to maintain some statistical information about the processes. Like for example, how much CPU time the process has already used, how much is the total waiting time of the process so far, and so on. Based on these, the dispatcher can decide which is the next process that should get the CPU. These are called CPU scheduling information, and of course, any other information can also be there. So, pictorially we can show the PCB like this, where of course, all the fields are not shown, some of the fields are shown. So, the relevant information about a process will be stored in a data structure like this in memory. Okay? Fine. Now, I had talked about context switch. This context switch is a very important part of this process state transitions, because the reason is that depending on the number of CPUs that are there in the system, only a limited number of processes can be in the running state. Limited number of processes can be running at a given time. Okay? This you must remember. So, there will be lot more number of processes which may be waiting to get the CPU, they are in the ready state. So, for a single CPU system, there will be a single CPU which will single process which will be running on the CPU, and all others will be waiting either in the ready or the block states. Now, we mentioned earlier, when a process is in the running state, it can invoke a system call, it can request for an IO operation, input or output operation. So, it will temporarily move to the block state. Similarly, a process in the block state which was waiting for some event, that event can occur and the process will move from the block state to the ready state. Similarly, in a time sharing kind of a system, when the time slice elapses, the running process can be forced to move to the ready state, and the next process in the ready state will be moved to the running state. So, there are so many transitions in the process states which are going on, and if you look into the PCB, you will appreciate that for each of these transitions, for the currently running process, all the relevant information must first be saved in the PCB, like the contents of the registers, contents of the open files, memory information, etc., all information, and the next process to whom you want to give the CPU, you have to load the relevant information into the registers and other places, so that it can start execution. So, this process is referred to as context switch. Context switch means temporarily stopping one process and starting another process, and because it involves saving and restoring so much information, this often takes a significant amount of time. So, there are many mechanisms that are proposed in modern day systems, so that the context switch overheads can be reduced to the extent possible. So, as I said, during the context switch operation, when some process moves out of the running state. So, when a process is in the running state, it was using the CPU registers, program counter was pointing to the next instruction. So, all such processor status information, the registers, must be saved into the PCB first, and of course, the other relevant information like files, memory information, etc. This is the first thing you must do. The process which was running, save its information in the corresponding PCB. Then some new process will be given to the CPU. So, some new process will be moving to the running state. So, the status and all other relevant information for that process which was stored in the corresponding PCB will now have to be loaded before the process is given to the CPU for actual execution of the instructions. As I had said, in many modern day processors, we have a large number of registers, 32, 64 or even more. So, when you want to save and restore so many registers, the process can be quite time consuming. So, you will find that in many processors, there are some special hardware support which allows fast context switching. Like one important hardware support that is found in almost all modern day processors is something called multiple register banks. the idea is very simple. The idea is, you see, inside a CPU there are so many registers, right. Let us say inside the CPU there are registers which are used for the running of a program. Now, in addition to the registers, there are several copies of the registers. These are called register banks. Suppose there are 100 registers, there can be 4 such copies of the 100 registers, 100, 100, 100, 100. So, when you are running a process, the register bank, which is the next one, can be preloaded with the register set of the next process which is supposed to run. So that when you want to switch from one process to another, you do not have to save them and load them explicitly, they are already loaded. You will have to simply switch from one bank to the other, that is much faster. Okay. So, many processors or CPUs have support for this kind of hardware based context switching. Now, whenever a context switching occurs, pictorially it can be shown like this. Let us assume there are 2 processes, P1 and P2 running on the system. So, initially the process P1 is in the running state, it was running. Okay. Now, during running, for some reason it has to release the CPU, maybe it has invoked a system call or some interrupt has come. So, whenever such a thing happens, the control moves to the kernel. What the kernel will do? It will first save the status of this running process P1 into the PCB, let us call it PCB1. Okay. And suppose the OS also decides that the next process to run is PCB2, is P2, process P2. So, it will be restoring the state of the process P2 from PCB2, right. Now, after this saving and restoring is done, now actually the process P2 can start its execution, it can start to run. During this time, the process P1 will remain idle, because process P1 has released the CPU, it is waiting for something. Now, again in the future, whenever this process P2 invokes a system call or some other interrupt has come, so again P2 will be suspended here. So, the operating system will save the state of P2 into PCB2. Let us say it wants to again give the CPU back to P1. So, it will restore the state of the corresponding PCB, and then it will continue execution from here. So, P1 will again move to the running state, and whenever this interrupt comes, P2 will move to the idle state. So, in this way it happens in the axis of time. Some of the processes move from the running state to some other state, some of the processes move to the idle state or come out of the idle state, but whenever this context switching occurs, this save and restore, this pair of operations must be done. This is the basic idea behind context switch. Okay. Now, I talked about the process queues, the lists that are maintained by the operating system corresponding to all the processes which are in similar states. Let us see a couple of examples here in this slide. There will be one queue for all the processes in the ready state, which is referred to as ready queue. Let us take an example that there are 3 processes waiting in the ready state. Let us say process 1, process 5 and process 7. So, the corresponding PCBs are connected like this in a linked list. So, these are the pointers I said pointing to the next one, and the last PCB is pointing to null, there is no more. And the ready queue, normally the operating system has access to the first PCB in the list, it is called a head, and also the last PCB in the list called a tail. Because depending on the scheduling policy, the operating system may like to select the first PCB or the last PCB to give to the CPU next. So, it is better to maintain a pointer to the first and also the last elements in the linked list. That is how these queues are typically maintained. Okay. Similarly, for the blocked queue, all the processes that are in the block state, they will be maintained in a very similar way. There will be one PCB for each such process that are in the block state. They will be all chained together in a linked list. The last one will be pointing to null, and you will be maintaining a pointer to the first element of the list and also the last element of the list. Now, I have also mentioned blocked queue is not one, there can be multiple block queues. Multiple means one per event. The processes are waiting for some event to occur, and for every such event there will be a separate such blocked queue that will be maintained. Because I mentioned earlier, whenever that event occurs in the future, one of the processes from the blocked queue, corresponding blocked queue, will be picked up and moved to the ready state possibly. They are now ready to execute. Okay. Fine. Now, let us see what are the typical operations that are carried out on the processes by the operating system, or the operations that are supported by the operating system. Now, the most important operations are to create a new process, and once a process is finished, how to terminate it. So, creation of processes and termination of processes. These are the two most important operations related to processes that are carried out by the operating systems. Now, the scenario is very similar in almost all operating systems, but the nomenclature and terminology that you are using here pertains to the Unix or the Linux operating system. So, in a Linux or Unix operating system, there is a concept of parent and child processes, parent and child. The idea is, let us say a parent process, let us call it P, a parent process is running. What the parent process can do, the parent process can continue its execution, the parent process can create a child process, let us say C1, and C1 will also continue execution, right. The parent process can also create another child process C2, C2 can also continue execution. So, all these processes, a parent, multiple childs which was created, they are all running as concurrent processes in the operating system. So, initially there was one process, now there will be 3 processes. So, there is a mechanism by which a parent or a parent process can create child processes, or even a child process can create further child processes. In fact, any process in the operating system can create further processes. So, as I mentioned here, a parent process can create child processes, which in turn can create other processes as well. So, in the system there will be a hierarchy of processes that will get created. Let us say from an initial process there will be some new processes created. One of the processes will be creating further processes, some other processes can be creating further processes, this process can be creating some more. So, like this is called a tree, where there is a initial node called the root of the tree, and there are levels of child nodes, and there is no cycle in this diagram. You move from top to bottom. So, you create a tree of processes. So, as you move from top to bottom, you have a parent child relationship. The initial parent can create a child. When the child creates another child, that child becomes a parent now. Okay? Like that it happens. Now, another point is that to uniquely maintain information about all the processes, each of the processes in the system is assigned a unique number or an identifier. This is called process ID and in short we call it PID. So, every running process or every process in the system, in fact not necessarily running, they can be the other states also, they are assigned a unique process ID, a unique number. So, with that number you can do a lot of calculations or manipulations. Okay. Let us first look into the creation of processes. In the Unix or Linux system, how does a new process can get created? See, in Unix like operating system, Linux is a type of Unix like operating system, all processes get created using the fork system call other than the first process. Okay. So, there is a system call called fork. This fork is responsible for creating new processes. Whenever a process calls the fork system call. Now, let us now try to understand when a fork system call is invoked, is called, what actually happens. Let us say a parent process which is running, it invokes the fork system call. Okay. So, we have mentioned earlier that a typical memory map of a process consists of 4 regions, can be more than 4, but minimum 4: text region, data region, heap and stack regions. So, a parent which is having these 4 regions is calling a fork system call, it is invoking fork. Now, what will happen is that after the fork system call is executed, a new process will get created. One copy out of these 2, one is the original parent. So, that the parent will continue to be there. So, this text, data, heap and stack, whatever was there, the same values will get copied, they will remain actually, they will be the same values. But a new process will get created, child, where the text region will be shared. Text means the program code, right? The text region will be shared, but all the other regions, data region, heap region and stack regions, for these new regions will be created in memory. The original values of data 1, heap 1, stack 1, they will be copied here. Okay. So, a parent was running, a child gets created, only the text region is shared, it is not copied to a new region, but the other regions, data, heap and stack, they become separate. So, now if a child process writes something into the data region of the parent process will not get affected, because now the regions are different in memory, right. So, what I mean to say is that the parent and child processes share the text region, which is the code, program code. The other regions are separate. This is the point to note. And once these processes are created, the parent and child process can execute concurrently. Now, in operating system, when you say that 2 processes are executing concurrently, it does not necessarily mean that the 2 processes are executing in parallel, because in the system there can be a single CPU, and if there is a single CPU, only one process can execute at a time. But we talked about the time sharing system, we talked about the multi-programming system. So, the CPU can be shared among these different processes. So, parent can be given some time, child can be given some time, again parent is given some time and so on. So, both the parents and child will be executing in an overlapped fashion, that may be the more accurate word. But however, if there are multiple processors or multiple cores in the system, then 2 processes can be running on 2 different cores or 2 different processors, and that is truly parallel execution, right. And when the processes are created, there are some mechanisms we shall see a little later, that the parent process can check whether the child process has finished or not. The parent has created a child. Sometimes the parent may want to know that whether the child is still continuing or it has finished its execution. Such facilities are there. Okay. Now, in Unix or Linux, there are some system calls which are there, which are specifically used for this kind of management between the child and parent processes. The parent can create a child, they can synchronize among themselves and so on. So, there are a few other system calls, but I am here mentioning the 4 most important ones. The fork I have already mentioned. The fork system call is used to create a new process. But one thing remember, I am using this term system call. System call means whenever a process calls fork, suppose you write a C program, a program in C or C++, from there you make a function call to fork. So, what happens? From fork there is a call to the kernel which is made, and the kernel actually creates a new copy of the process. The user program cannot directly do that, right. It has to make a request to the kernel and the kernel will do it on behalf of that request, fine. So, the system calls are used in that context because they will involve some call to the kernel module finally, and the kernel will be doing the requested operation. Okay. And there is another interesting system call and also very important called exec, and exec is not one, there are a number of variations of the exec call, exec LP, exec V, exec VP, there are many such calls similar, but there is slight difference in the way they work. Now, this exec system call is typically used after the fork system call. Let us try to understand. You think of a child process that gets created after a fork. So, in the child process, as I said, there are 4 regions. One is the code region, text, data, heap and stack. So, one thing I mentioned, whenever this process gets created, the code region is shared with the parent. Now, in that code region, if there is an instruction exec, using exec you can call a new program, When you call a new program, what happens? This original text region gets overridden by a new thing. Everything gets overridden by a new memory regions corresponding to the new program. As if you are calling a new program, and whatever is required by the new program, that will overwrite the existing segments that we have, text, data, heap and stack. They will all get lost, and new copies corresponding to the new program, they will get stored in the place. That is what is done by the exec system call. And for the purpose of synchronization between the parent and the child, there is a system call called wait. Using wait, the parent process can check whether the child process has terminated. Okay. And when a child wants to terminate, it can invoke the exit system call, and it also can send a status code back to the parent, so that the parent will know whether there was any error in the process of execution by the child or the termination was normal. Different types of error codes or status codes can be sent back to the parent. Okay. Pictorially, the process of this fork, wait and exit by a parent process and a child process is depicted in this diagram. Let us see. So, here we are showing it pictorially, we are not showing the whole program. Suppose a parent process was running, instructions were executing, and one of the instruction, let us say is like this, PID equal to fork. PID is a variable and fork is a function you are calling. The function is returning some value and that value is stored in PID, right. Now, after this fork is called, as I said, a new process will be created, the parent will continue and a new child process will get created. But now remember, I said initially both the parent and child will be sharing the same text region, same code region. That means both will be executing the same code. So, how do you tell that this child should be separate from the parent? This is mentioned by the return value of the fork, this PID value, let us say. For the child process, the value of the return value will be 0 and for the parent process it will be greater than 0. In fact, it will be the process ID of the child, which is some number. So, after fork, if you just write a statement like this, if PID is greater than 0. So, PID greater than 0 means it is the parent process. Then you write some code, this is for your parent process. Else you again write some code, this will be your child process. So, by checking the PID, you can write two segments of code in the same program. One of them will be corresponding to the parent, one of them will be corresponding to child. So, both the parent and child will not be executing the same code. One of them will be executing this part, one of them will be executing this part. Okay. Now, typically the child process invokes an exec system call to call an external program, and that external program, whatever it is, it will override the 4 regions, as I said, of the child process. And inside that program, whenever the child process finishes execution, normally the last statement will be an exit. And the parent process, on the other hand, can have a wait statement in somewhere in the code. So, when the parent invokes a wait statement, it will be waiting there, it will be temporarily paused, it will be waiting for the child to terminate. As soon as the child executes the exit system call, it will terminate and the parent will wake up, that wait system call will return. So, this exit and wait has a inherent synchronization between them. Okay. The wait system call makes the parent process to wait till a child process terminates, and when a child process terminates, the parent process resumes execution after that wait statement. Okay? Fine. Now, let us look at a complete code example in C, how we can use this fork system called create processes and so on. So, for those of you who are familiar with C programming, it will be easy for you. So, normally in a C program, in the beginning we include the standard IO library stdio.h, but here for using fork you will have to use 2 more libraries. One is systypes.h, other is unistd.h. This fork is actually part of unistd.h, and systypes.h some data types are defined, new data types. Now, this main function starts. In this systypes.h, one data type that is defined is PID underscore T, that is actually the data type of a process ID. It is nothing but an integer really, but in that header file it is defined with a special name PID T. So, let us say we define a variable my PID, which is supposed to store the PID number. Then I execute this fork and store the return value in my PID equal to fork. Now, in this program I have not shown, but remember one thing, if there is some problem due to some memory limitation or some other error, the kernel was not able to execute fork correctly, then fork will return a negative value. But in this program we have not checked for negative value, that you can do if you want to, that if my PID is less than 0, then print some error message, then exit. But here we are checking if my PID equal to 0 or not. Equal to 0 means I said it will be the child process, the PID will be 0 for the child process, it will be greater than 0 for the parent process. So, if it is a child process, I said the child process can invoke an exec system call. I am giving one example, this is exec LP, one system call of the exec family. So, exec LP takes 3 parameters this function. One is the path name of the command you want to execute, myprog. Second one is again the same thing, the name of the program, myprog, and third parameter normally you do not give anything. There are some options I am not discussing here, you can give null. So, what will happen? Myprog is an executable program already stored in that path home ISG myprog. That program will be loaded by the operating system and a new process will be created, and the child whatever was there, that will be overwritten by that new memory map, text, data, heap and stack. So, now the parent and child will be entirely 2 different processes, nothing sharing, entirely 2 different processes. And when you come to else, this is actually the parent process. Here you can invoke a wait system call if the parent wants to wait. So, the child will execute whenever the child finishes, an exit will be executed at the end. Now, this wait, the parent will come out of the wait, it will go to print, child process complete. This is what happens, right, in this program. Okay. Now, let us look at one thing. I mentioned that you can have a fork system call by a parent. Suppose this is a parent. So, whenever you execute a fork system call, what will happen? The parent continues and a new child gets created. Now, the child can again execute a fork, let us say. So, after fork again this child will continue and a new child C1 will get created, like this it continues, right. So, every fork statement will have 2 processes after that. Initially it was 1, after one fork it will be 2. Let us say in a program I write 2 fork statements one after the other. Let us say PID 1 equal to fork, PID 2 equal to fork. There are 2 statements one after the other. Let us understand what will happen here. The first fork statement will execute. So, there will be 2 processes which will be created, one parent, one child. Now, in this program we are not checking whether P1 is 0 or P1 is greater than 0, right. For both parent and child it will continue with the next statement. Next statement is also a fork. So, the parent will also do a fork, the child will also do a fork. So, now we will be having a total of 4 processes. So, if I have another fork after that, so each of them will be having 2 each, there will be 8 processes. So, if like this one after the other, if you have n forks, then there will be 2 to the power n processes created. This is just for your interest. So, if you do not check anything, the number of processes can grow exponentially, 2 to the power n, it is very large, right. Okay. Next, let us come to the issue of termination of a process. how do you terminate or stop a process? I said that there is a exit system call which can be explicitly called, or whenever a process executes its last statement, exit is implicitly called. So, when you write a program, it is not necessary that you will always have to give the exit system call. The compiler, when it is generating the executable code, it will automatically insert an exit after the last statement, right. Now, in the exit system call, if it is called by a child process, then it can return a status code which may be used by the parent to know that what happened in the child. And as I showed in the diagram previously, the parent process can be waiting on the wait system call. The point to note is that whenever we execute such an exit system call, a process, then all the resources the process was holding, like memories, all the files that are open, the locks, if it has acquired some locks on some variables, we will see those things later. So, all of these will be released, so that any other process who wants to use can use them. Okay. This is the normal way of termination of a process. A process executes an exit, or it executes the last statement, there is an implied exit, process terminates, and a parent process can wait for the termination by executing a wait. Now, there is another way. It is possible that due to some reason the child process is not exiting, it has gone into an infinite loop or something. So, a parent process can forcibly terminate a child process also by calling a system call called abort. This abort may be called due to multiple reasons. One may be, as I said, the child process has got stuck due to some reason, it is not coming out, or due to some reason the parent process has to stop, and it wants that all the child processes that I have created must also stop. So, it will abort all of them. Okay. Now, the wait system call can be called like this: wait, you return the address of a variable, ampersand means address, the name of the variable is return status, and it returns a value. See, there was a parent, possibly the parent has created multiple child processes, let us say child 1, child 2. Suppose child 1 has a PID of, let us take an example, PID of let us say 1000 for example, let us assume, and child 2 has a process ID of let us say 1004. Okay. Let us say the parent has made a call like this, child PID equal to wait ampersand return status. So, either child 1 may terminate first or child 2 may terminate first. So, one of them has executed the exit. So, the parent, so when it does an exit, let me tell you, in exit there is a parameter, it can give a value number n. So, this number n will be returned to the parent. So, let us say the value of n was let us say 1. So, this 1 will go to this return status, the value of return status will become 1. And which child process terminated? It can be child 1, it can be child 2. If child 1 terminated, then the return value of wait will be 1000. This child PID will be 1000. So, the parent can check the return value, the child PID, and know that which of the two child processes actually terminated, whether it was child 1 or it was child 2, right. Okay. And there are a couple of two special processes, means I would not say special processes, we give some special names to these processes. We refer to them as zombie processes or orphan processes. See, zombie means a process has finished execution, but the parent process was still running, it did not invoke wait. So, due to some reason, because the parent has not yet stopped, the operating system had still not removed information about the process from the system. The process is not there, but the kernel table somehow still maintains some information about the system. That is referred to as a zombie process. But an orphan process is slightly different. It says that child process is running, it is still running, but due to some reason the parent process has terminated. The parent process did not use the wait system call, so it did not check whether the child had terminated or not, but the parent prematurely terminated, but the child is continuing. Such a process is referred to as a orphan process, that means a process which does not have a parent, right. So, these are two special names given to two special kinds of processes, zombie and orphan. Now, as I had said lastly, that you can have this like let us go to the previous slide, this wait and the exit system calls. So, let me give a very specific example here, the parent and any one of the child. So, here we can define a variable PID t as let us say x y z. This is a variable I define in C, which is of type process ID. Now, the parent what it can do, it can not PID, it can write x y z equal to wait ampersand some return value, let us say a. So, here we can define another integer a will be some return value. Now, in the child what it can do, the child there can be different conditions inside the child was supposed to execute something. So, depending on a condition, suppose it checks something, depending on some condition it does a let us say exit 0, else it does an exit 1, let us say something like this. So, the child value is calling exit to terminate itself, but it also specifies a return value 0 or 1. Now, in general it can be any value, I have only shown two values. Now, this return value will be returned to the variable a. So, later on if I want to print the value of a, let us say printf percentage d means integer a, then the value of a will be printed either 0 or 1. So, the parent will know whether the child has terminated with exit 0 condition or exit 1 condition. Let us say exit 1 condition may be some error condition, exit 0 may be normal exit, something like that. And of course, I told earlier that the child PID whatever it is there, the PID of the child that will be returned as the return value of wait into the variable x y z. So, x y z will contain the return value. So, see in this way using the system calls in a program you can manipulate or you can synchronize among these concurrent processes, a parent, child, so many of them, right. But one thing you now try to understand, which we will be discussing in the next module, that in general the system can contain a number of processes, because any of these processes can invoke fork and it can create new processes. There can be many processes running in the system, they will be running something, doing something. Now, for a particular application, the processes that are created they are usually not independent processes. They must coordinate among themselves to carry out a certain specific task. So, they need to communicate among themselves, they may need to share some common variables, common data, and so on. So, in the next module we shall be seeing that how these processes can communicate among themselves, how the process execution can be synchronized. For example, I may say that process P1 will execute up to that point and will wait till process P2 sends some kind of a signal, so that it can again resume. This kind of synchronization may also be required in many examples, and also when you are accessing some shared variables, you must be very careful, because when accessing shared variables something may get wrong. We shall be seeing all those things. But another thing is there, in addition to processes, we have the notion of a thread that we will also be discussing in our next lecture. Thank you.